OpenACC is a directives-based approach, very much like OpenMP, but it's not magic pixie dust. It will not obviate the need to be able to understand a lot of the concepts that Jeff just went over. And you'll see the parallels throughout, I hope you'll see the parallels throughout this presentation. So the interesting thing about this paper, and you can find it for yourself on archive.org, it was written back in '99. The authors are all my contemporaries, and in fact, I still know a lot of them. Chris Gottbrath works for what used to be Total View Technologies. He does debugger work. Jeremy Balin just moved to the University of Alabama. Casey Meakin works at Los Alamos. Todd Thompson's at Ohio State. Asked me at lunch about J.J. Charfman because it's a great story about J.J. But they actually put this paper on the preprint server. And what they noticed was they were doing very, very large simulations. You guys, Sean Couch gave a talk about core collapse supernova simulation, right? And it takes forever. I mean, that's one of my research interests. And I have a core collapse supernova simulation that's been running for literally 8 months now. And it'll keep running for another 4. All right, so it takes forever. So really, really large-scale computations. What they noticed is because back in the days in the late 90s when Dennard scaling and Moore's law were sort of synonymous with one another, and you were getting huge clock speed ups, that what you really should do, if you had a job that maybe was going to take 2 full years from the time you really started developing the code to the time you got finished, you really should just slack off for about 24 months because you'll end up at the same point anyway because Moore's law will increase this slope of this rate of getting work done. So it really wasn't worth your time to work hard for those 2 years. You really should just let Moore's law keep up. Unfortunately, because I'm lazy, this doesn't obtain anymore. And the reason it doesn't obtain is Dennard scaling and Moore's law aren't synonymous with one another anymore. They're not the same things. We're not getting clock speed increases like we used to back when I was a grad student. Furthermore, this brave new world is right now. And it really is the future. You're seeing all of the near future written in microcosm right now. And that all near future systems, I don't care if they're GPUs or something else yet to be named, or if they have names like Phi, will have secondary memories that are as large as we currently require, things like DRAM. However, they'll not have those things won't have high bandwidth to the principal computation engine, which is, for example, the accelerator. There will be a smaller, faster memory that will still supply the principal compute engine. You see that, right? That's the texture memory, for example, that Jeff just told you a lot about. And while system software may manage the 2 memories, if you really want to get good performance, you have to learn how to manage those 2 memories yourself to some extent. An explanation of, in this context, what is the difference between the secondary memory and a cache? And so, for example, being directly user addressable and or being just bigger than a traditional cache. You can certainly, probably usable as a cache as well. And of course, we have a driving force to understand GPUs at Oak Ridge, and you've seen this slide before, this feeds and speeds for Titan, which is currently the world's 2nd largest supercomputer. The GPUs themselves have an order of magnitude more flops available in them than the CPUs. And there's a lot of memory on each one of these cards. The individual GPUs are the next generation beyond the Fermis that are in Keeneland, and that actually presents some interesting tricks that you can play relative to Keeneland. I think everybody will have access to Titan at some point next week. And later in the talk, I'll make reference to some Cray-specific stuff and actually some capabilities of OpenACC that depend on having the compute capability that we have on Titan with the Keplers. So you may have to wait to try some of the hands-on examples until then. I know at this point you've heard about MPI, we've talked about OpenMP, we've talked a little bit about CUDA, and Bill Gropp this morning told you about forming hybrid codes. I think the point is the hybridization has to be something that you're going to have to think about from the get-go now, and it's going to have to be ubiquitous in everything you do. Because ultimately you're going to want to use something like, and it doesn't necessarily have to be this recipe, but something like MPI-type parallelism between nodes using domain decomposition, or use a PGAS to do distributed memory parallelism. On-node SMP-like parallelism via, for example, threads, OpenMP would be a good example, and then some sort of vector parallelism, whether that's in using vector operations on the CPU, for example, SSE or AVX on an Intel Phi, or marshalling GPU threads in parallel in a SMT-like thing, but to a user it looks like vectors. And it's the exposure of all these levels of parallelism that's actually going to give you good performance. So you need to, taking bytes here and there and only doing part of this hierarchy probably is not going to get you the performance that you ultimately want to get you your problem done as fast as possible. And uncovering unrealized parallelism and improving data locality improves even the performance of CPU-only code. So when we decided to field Titan, we started this thing called CAR, which is the Center for Accelerated Application Readiness. We took just a handful of codes, put people to work on them over the span of about 2 years. They didn't spend all their time over those 2 years, but they spent a good chunk trying to port them directly to Titan using CUDA and OpenACC. But we kind of grew up with the evolution of those standards. The total time window was over 2 years. And what we found was that the median, both the median and the mode speed up, on the CPU-only code that got produced was 2x. So if you compared the code when we started and compared the code when we finished and just ran code on the CPU, you got a 2x speed up. And it was always 2 to within one significant figure. Most of that's from good cache reuse. It's because you're forced to pay attention to memory access patterns when you use a separated device like a GPU, whereas maybe that's something you put off in your CPU-only code. The point here is that any effort that you expend to harness an accelerator, for the most part, will not be wasted because most of the work is restructuring data structures, refiguring loops, hoisting things out of subroutines, work like that regardless of how you ultimately marshal the GPU, be it CUDA, OpenCL, OpenACC, something else that doesn't exist yet, it's going to be time that's not wasted. Think about, for example, I'm assuming that everybody works on an MPI code in here. You can probably, if I pushed you really hard, count on all your fingers and toes, all of the routines in the code that you work on that actually have MPI calls in them. There's probably no more than 20, even in big codes, maybe 40, okay? But there's not 400. The same thing happens when you do GPU programming or accelerator programming for very, very large codes. Just to reiterate, so what do we want to do? We've got to have good threading. The OpenMP is a good choice. And the most important thing here is making sure that the load balance between the threads is good. That's what's going to ensure good performance. And the second thing is good vectorization. The vectorization advantage, usually, if you do it well, or can get the compiler to do it well for you, allows plenty of time for introducing the overhead. And vectorization that doesn't rely on having the hardware that is described as vector. Again, you can have code that vectorizes, but is actually running on a SIMT-like device, like a GPU. So a lot of what follows, I just wanted to drop this in to make sure everybody understands. I've stolen wholesale from a handful of people. If you really want to learn a lot about OpenACC, you should Google these people's names and their affiliations, because between the three of them, have given tons and tons of presentations on OpenACC and GPU programming in general. Matt Colgrove at PGI, Jeff Larkin, who's now at NVIDIA, who used to be at Cray, and John Levesque, who's also at Cray. So just Googling those guys' names will provide you with a wealth of information that you might not otherwise have. And they've been a big help in preparing this. So what is OpenACC? Well, just like OpenMP, which you heard a lot about yesterday, it's an attempt to standardize a way to have directive programming for the current generation of GPUs. It doesn't have to be GPUs, and we'll talk about that in just a second. It was announced at the Supercomputing 11 conference. You've heard about supercomputing today as well. The reason that you want to have a standard is so that compiler vendors and writers can have a standard to program to, so that the use and the availability can be ubiquitous for this. It was originally drawn up by NVIDIA, Cray, PGI, and a French company called CAPS. And the multiple compilers offer portability and debugging and hopefully some sense of permanence for the standard. It works for Fortran, C, and C++. As in all things in HPC, the C++ support isn't as good as it is for the Fortran and C. And there are reasons for that, of course. So the same sort of reasons that you usually get problems with C++. The object-oriented nature of what you're doing obscures some of the things that you really need to get at to be able to enhance performance, and therefore it's a little bit harder. The current version is version 1.0, which was established in November 2011. There's a new standard, 2.0, coming out, and we'll talk about that closer to the end of the talk. And the current state of the compiler support is the Cray compilers, which are available on Titan, but nowhere else. Well, not anywhere else, but only on Cray machines. They're like Mac OS X, is a complete implementation of the 1.0 standard. PGI Accelerator also has a complete 1.0 standard compliant implementation, plus extensions that PGI has added. So PGI had their own accelerator extensions before OpenACC was actually standardized. So the set of possible directives that you have available with the PGI compiler is actually OpenACC plus Epsilon. It's actually bigger than the set that's in the standard. And the same thing with CAPS. CAPS also had their own ways of doing directive-based accelerator programming before OpenACC became a standard, and therefore their implemented set is the whole standard plus some other things. So you may find in each of those cases that some of the PGI extensions or the HMPP extensions are good things to use and are very amenable to your particular problem, but keep in mind, if you make use of them, the code that you finally end up with may not be completely portable. Hopefully that's not such a big deal for reasons that we'll get to in just a little while. And then specifically, why do you want to use OpenACC Directives? Well, it's a higher level programming model. It ought to be easier to write, just like OpenMP. And it should provide you portability. You have the ability to ignore the directives because they're directives, and therefore the code should be portable just on a host box, the CPU only. It should be portable across different accelerators. There are backends that generate CUDA kernels. There are backends that generate OpenCL kernels for use on AMD chips. HMPP, in fact, has a backend that generates code for the Intel feed. And you should have fairly good performance portability if each of those backends does their job correctly. You also have the ability to get performance feedback at compile time. At least the compiler can tell you what it's doing and how good a job you've actually done in expressing what you want it to do at compile time. I consider this fairly important. So take a matrix multiply code, and I've made the code way too small, you actually can't read it. But I can implement it with directives over there on the far left with just a handful of lines. If I implement the same code in CUDA-C, maybe I double to triple the size of the code. And if I do it in OpenCL, this is what I end up with. OpenCL, because it's such a powerful thing, demands a lot more typing. And again, as I said earlier, I'm lazy. I don't want to type this. That's not a good enough reason to use OpenCL. But perhaps a good enough reason is with this much typing, it's very easy for a human to make mistakes. And so especially when you're working with very, very large code bases, this is not an insignificant consideration. The fewer lines of code that you can produce and have to maintain, the better off you often are, unless you get some raw performance enhancement by actually doing this much typing. And there's problems invariably that happens. But Jeff showed you a set of benchmarks that for a variety of directive-based approaches can achieve the same sort of performance that, for example, hand-coded CUDA can. For most platforms, OpenCL and hand-coded CUDA are roughly comparable to one another. So if the transitive property sort of works, directives-based code should be roughly equivalent to OpenCL code. Okay, so there's a whole set of risk factors that you might want to consider before you jump headlong and become an OpenACC programmer. Will I have machines that I can run my OpenACC code on? Well, right now there's tons of them. There's the big machines like these XK7s, the Toady machine at CSCS in Switzerland. There's a machine in Stuttgart called Hermit, and of course Titan. Lots of other GPU machines in the top 100, and lots of people have their own GPU clusters setting in departments and work groups throughout the world. Again, what about if I want to keep my code fairly future-proof? Well, again, there's going to be targets, back-end targets that vary from all kinds of different GPUs to Intel fees to whatever else comes down the pike to some extent, because again, the basic fundamental architecture is not going to be able to change that much. Modular things like having stacked memory or something like that. And you can always just run it on a CPU if you have a fast CPU. Right? If you get your hands on the latest, fastest GPU, you can also run the same code base without modification on a CPU only. Will it continue into the future? I think it will. It may in fact become subsumed into OpenMP, and there will be a little bit of translation as that sublimation happens, but it'll continue. In fact, it's developing right now at a faster rate than OpenMP. And part of that is because the sheer number of people who are involved in establishing the standard is fewer. So the level of accord that you have to reach between partners is somewhat less. You can almost get all the standards body into half of this room for OpenACC, and for OpenMP, I think we would have to take over this whole building, for example. Will it be superseded by something else? What if we get this magic compiler that I want to be able to use to do supernova simulation? Well, anybody from New York? So my PhD advisor was from Staten Island, and whenever he would find me saying something that he didn't really believe, he would look at me and say, good luck, here's $5, right? And that's sort of the story with a magical auto-vectorizing compiler, okay? It's like fusion energy, right? We've been waiting for it for 20 years, independent of time. It's just around the corner. I wouldn't put my eggs in that basket. OpenMP accelerator directives? Sure, but any work that you do with OpenACC today won't be wasted. Again, most of the work is restructuring data structures, refiguring loops, hoisting things out of subroutines. You have a finite number of contact points with the underlying API, and guess what? They almost have to look a lot alike syntactically. How can you express some of these things if you don't use a lot of the same words? I think a well-formulated SED will be able to do the replacement for you, even if something changes as things become subsumed into OpenMP. This is just a slide sort of recapitulating in graphical form what I've been telling you over and over, that really OpenACC is, in its current implementation, is directed towards GPUs. It's really built on top of this sort of abstract machine architecture, where you have an accelerator out here with some sort of device-optimized memory connected to a multi-core CPU with some latency-optimized host memory over there. We have paths for data between the two memories, and you have control being exercised by the multi-core CPU, and some number of execution queues, whether those are warps on a GPU or OpenMP threads on Intel Phi is almost immaterial. What happens when you actually compile a piece of OpenACC code, you end up getting two sets of machine code that are both linked for the executable, and you have what's called a unified executable. Usually through setting an environment variable, you can tell the runtime whether or not you actually have a device for the target device code to actually run on, and if you don't, it's ignored. But you'll see that the executables can be significantly larger than they are in the case of without OpenACC. So don't be alarmed if suddenly the size of your executable bubbles. Usually it's just it'll just be the static construction part. You know, there'll be a handful of extra buffers, but the model in OpenACC is to use dynamic memory allocation, so you don't have to worry about that actually bloating your accelerator. All right, so we can look at this code. There's a pragma that declares that we're in a data region for the accelerator. I'm going to tell the compiler that I want to copy B and create A. Copy is a clause in the accelerated data directive that says allocate room for B on the device, copy the host version of B onto the device, and when you get done, ship it back to the host and free the memory on the device. So copy is a very overloaded thing. It actually does 4 distinct things. Create, all create does is allocate room for A on the device. That's all it does. All right? Then you see a nice triply nested loop here, and then a reduction here at the bottom. This is some sort of smoothing kernel. All right? And all we've done is say pragma accelerator kernels, telling the compiler to take a look at the set of enclosed loops below in C demarked by the extra set of curly brackets. So this is the advantage that one advantage that C has over Fortran. In Fortran, you have to put a start sentinel and an end sentinel, right? Whereas the curly brackets in C allow you to just put a single sentinel to start the operation. And it tells the compiler, go crazy, go nuts, try to figure out if you can actually form GPU kernels out of these triply nested loops. And if you can, tell me if I've thrown the -m-info flag, for example, on the PGI compiler. Tell me what you've done. So as we step through the execution, you can actually see what's done. The first step, after we do that copy and create, is now there's a slot for A and a slot for B. B is empty right now. We haven't actually put anything in B. But I copy over all the zeros, for example. Then I go to the first iteration of this triply nested loop. The compiler has taken the triply nested loop, formed a GPU kernel out of it, and computes that smoothing operation over B. It does that for that first loop nest. Then it copies that result, which is stored in A, on the device into B for that second loop. And then it just keeps iterating this loop over and over. Gets S2, copies S2 over. Keep going. You can see where this is going. I hope. S of P, right? So this is where I'll stop. Then the last thing, when I'm done with all that loop nest, it copies B back. Remember that I use the copy clause for B, which means allocate, copy over, copy back, deallocate. A really overloaded thing. So it does all 4 things. It also deallocs the memory it had for A and deallocs the memory. So a lot of code went on. You could almost see, if you were to if you could sit down with Jeff's presentation and this slide in animation, you could almost figure out clause for clause how to do that in CUDA fairly straightforwardly. But you didn't have to write the CUDA kernel to actually do that triply nested loop. The beautiful thing about OpenACC, as you might expect from a directives-based approach, is that you only need a handful of constructs in your arsenal to be able to do at least simple things. And then when you discover you're not getting the performance that you want, you can sort of add to your knowledge and add constructs. So the very first construct to understand, and it's just like doing OMP parallel, right, is a couple of compute constructs called kernels and parallel. The most implicit, highest level one of those is called kernels. And you see the way that it's actually implemented in C and in Fortran here. So the same kind of sentinel that you see for OpenMP directives, and you have a kernels clause and an in-kernels clause. You'll notice that we used the kernels construct in that example that I showed up before lunch, right? And there were actually two sets of nested loops in that example. What the kernels construct does is take everything in the enclosed section, and it's enclosed if it's inside the curly brackets for C, and is marked, the close is marked with an ACC end kernels in Fortran, takes all of the enclosed code and generates as many kernels as it needs to effectively move the work out to the GPU. And that can be one kernel or many kernels, depending on how many sets of nested loops that you have. So this is sort of a trivial example, right? This is sort of using kernels when you could easily use another construct called parallel. You can see things look a lot the same. There are tons of things you can do to tell the compiler how you're going to schedule the enclosed loop or loop nest. Okay, we'll get into that in just a second. The details of actually using these clauses in the individual loop structure. The easiest thing to do is to remember sort of the difference between kernels and parallel is really a difference between letting the compiler have more control or less control. If you want to enclose a large section of code that consists of almost nothing except sets of multiply nested loops, go ahead and use kernels. Give it a try. You can use that as the baseline for comparison for the kind of tuning that you do later. This kernels construct, these are PGI supplied slides, so they claim that it's derived from the PGI accelerator model. It's more implicit, like I said, giving the compiler more freedom to create the optimal code for a given accelerator. And kernels, for example, will often, if you have a reduction, we talked about reductions earlier, if you have a reduction at the end of whatever kernel you're doing, using a kernels construct will usually generate good code for that reduction at the end. So that's, you know you have a reduction coming at the end of what you're going to be doing. Using kernels is often a good thing. You may have to give the compiler more hints. And a good example is you may have to use restrict. Raise your right hand and solemnly swear I will not alias any pointers, right? Because that can easily confuse the compiler about what it can or can't do as far as host data is concerned and moving host data from the host to the device. The parallel construct is a lot like the OpenMP work share down to having things like gangs and workers and tasks. The important thing to remember is that what the parallel construct does is it creates parallel gangs and they do the work inside the loop completely redundantly. If you don't tell the compiler how you're going to decompose the loops after you use the parallel construct, it'll just do the same thing in the loop body over and over again. You have to give it some scheduling information. And that leads to that last comment. It's more explicit and therefore requires a little more attention on your part. There's an article online at the PGI website that gives a little more detail about the differences between the two constructs. That's the compute construct. That's basically telling the compiler, this is the block of code that I want to move to the accelerator. Let's talk about loops. So like we said earlier, when you use parallel, you need to give the compiler information about how you're actually going to schedule the loops. Here you see the two syntaxes for C and Fortran. You can combine the compute construct and the loop directive on the single line. So you could, for example, say bang $ACC parallel loop gang, all in one line. They can be fused together. That reduces the number of lines of code that you're actually having to touch to get the job done. So there are a handful of these clauses you can use. One's independent. Independent is like a lot of compiler options that you may have seen or compiler hints that you may have seen. What it says is it overrides the compiler analysis and says, no, damn it, I know that the iterates in this loop are independent of one another. Please parallelize it for me. Even if you can't figure out that they're independent iterations, I promise that they are. Okay? There's a problem there. It's not really a problem, it's just something you have to remember. When you say that, right, the compiler picks its ball up and goes home. It says, okay, fine, screw you, I'm going to make them all parallel if it's a nested loop. Okay? If you have a triply nested loop, usually maybe that inner iterate isn't independent. It needs to be vectorized. Typically, you'll have to put, say I had a triply nested loop, you'll have to put loop independent around one, the outermost, you'll have to put loop independent around the second loop, and on the innermost loop, you'll have to use SEQ, sequential, execute that loop sequentially. It's just a matter of remembering that once you sort of turn off the compiler's smarts, however dumb they are, it quits and says, fine, do what you want. You can also specify the private data for the list. This is very akin to what you do in OpenMP with shared and private data in a loop nest. And you can also tell it, give it a hint that you're actually going to do a reduction. And then there are different scheduling classes, vector, gang, worker, or like I said, sequential. We can go a little bit into those. Gang scheduling, it's the highest level of parallelism. And it's equivalent to a CUDA thread block. So you're essentially assigning the iterates due to that loop to individual CUDA thread blocks. And I noticed that in my presentation and in Jeff's presentation, the one thing that we don't have is this canonical picture of a grid block and then a block ID with block threads and then threads and a 2D thread block. But everybody raised their hand and said they'd done some GPU programming, or almost everybody had, so I'm assuming you've seen pictures like that before. So this is sort of the first level of box underneath the big box that sort of contains the whole device, the thread blocks. And another way to say that is a gang loop affects the CUDA grid, okay? The grid of all possible thread blocks that are being launched in a kernel. Worker scheduling, that's an individual member of the gang. So comparison, an analogy to CUDA thread block, that refers to each one of the CUDA threads within that thread block. So an individual worker in OpenACC can be immediately mapped directly to an individual CUDA thread that's a member of a thread block. Same sort of communication notions that obtain between threads in a thread block or threads that are not in the same thread block also obtain here. That is, workers in a given gang can easily share data. Workers that are in separate gangs are assumed not to be sharing data. And again, another way to say that is the worker loop affects the CUDA thread block. And vector scheduling is the tightest level of SIMT or SIMD or vector parallelism, and it's basically equivalent to a CUDA warp. We didn't mention warps in the CUDA talk earlier. That's a hardware notion, and it's basically the number of individual threads that get updated all at once. So you have these three, and if you use them strictly, top to bottom, if you had a triply nested loop and you had gang scheduling for the outermost loop, worker scheduling for the second loop, and vector scheduling for the innermost, this sort of analogy would hold all the way through. And declaring these on particular loops in your loop nest will affect the decomposition of the problem to the hardware, actually. If you don't apply it sort of consistently from outermost loop to innermost loop, the mapping's not quite as clear. And so I've got a couple of examples of that. So for example, if I just had accelerator loop gang, well, that does just what we said, right? That means that individual thread blocks are assigned to iterates of the loop over the block index. It doesn't declare that the loop is in fact parallel. You may have to tell the compiler, no, really do it. It won't necessarily schedule it as parallel just if you put ACC loop gang. Okay, that's not equivalent to having an independent in there. Or you can give it the number of thread blocks that you're actually going to use, in this case 32. If you just have ACC loop vector on a single outermost loop, that would actually run it in vector mode with a block dimension of 128. That means there'd be 128 individual threads within a thread block, and one thread block would be one iterate of the loop. Okay? So it kind of has muddled this mapping that we have of gang to thread block, worker to thread, vector to warp. Okay? It's sort of pulled that up. It's sort of offset these levels of parallelism when you use these by themselves. You can string them all three together, loop, gang, vector, 128. This effectively strip mines the loop. It means that the inner loop runs in vector mode with 128 threads operating on that thing, okay? And the outer loop runs across the threaded blocks. You have a lot of control with the loop scheduling clauses about how you're actually going to implement the parallelism. A lot of that, which one of these you use, depends on the data locality and how much computation is actually in the body of the loop. Sometimes you just have to play. Sometimes you can only figure out what the best scheduling formulation is only empirically. Okay, so we have basic compute constructs. We have thoroughly confusing loop clauses and scheduling clauses. The one thing that we're really missing on the device is a way to get data out there. And in CUDA, you just do CUDA memcopy. There's also some other functions, but that's the primary one. In OpenACC, we use the notion of data regions. You basically just put a sentinel at the start of a data region and at the end of a data region, for example, in Fortran. You can span them across host code and multiple compute regions, okay? You're just basically setting the default home of the data that you're going to declare inside the pragmas with these data constructs. So if, for example, I have the first sentinel ACC data, everything that I declare will be a data variable until I say specifically it's a host variable. You can therefore intersperse, you can nest them. What you don't want to do is offset them, right? You don't want to have an accelerated data region with another accelerator data region starting and then they end at different places, okay? That's the one thing you can't do. You can nest them though, but you can't nest them inside a compute region because you need to be able to consistently say what kind of data that you're going to operate on. Importantly, just because you declared a data region, the data is not implicitly synchronized between the host and the device. Anytime you use a compute construct, there is a lot of implicit synchronization between the host and the device. We showed that in the first example when we had B as being set to copy, and then anytime we had an accelerator kernel that was going to operate on B, we had the copy out to the device, management of the variable when it was out there, and then a copy back, and all of that was essentially implicit after I said copy and ACC kernel. Just because I declare a data region, however, that doesn't say anything about how I'm going to do the synchronization of the data between the host and the device. And in fact, you have to have some new sentinels to handle that in the form of clauses. They do just what you would expect. You can copy out to the device. You can copy out to the device only at the start of the parallel region. That's what copy in means. Specifically, copy in means don't copy out. Copy is this overloaded thing that we referred to in the first example, where we copy the data in, operate on it, and copy it back out to the host at the end. Copy in means just copy in the data that I need, but leave it on the device. Don't make me pay the penalty of sending the data over the PCI Express bus in the case of a GPU, because I don't need it on the host code anymore. I just need to give it, or maybe the next time through the loop, I'll need it on the device, okay? Copy out means that it's over there on the device, I think. Just copy it out when you get done, because I actually need the result of the calculation. Create is essentially a malloc. It's easy to think of it that way on the device itself. So you allocate space on the device for a variable that you're going to actually dynamically size later, usually. Present and the ones that derive from present. Present or copy in, present or copy out, present or create, etc. are very useful. And I suggest using present or copy in instead of, for example, copy in, because it's good defensive programming. What those particular clauses do is ask the question, is the data present on the device already, for example? If you use this one, and you can abbreviate all these with just pcopy, pcopy in, pcopy out, and pcreate. The first one, for example, would ask, is B already on the device present? If it is, don't do anything. So if you don't think you have to copy in, or there's a chance you might not have to copy in, go ahead and use that. Now you have to be careful about the state between the host and the device when you do this. Right? You don't want to make copies in places, or you don't want to think that you've updated a device or a host copy when you really haven't. For the most part, for a lot of data structures, you can do this kind of thing. Same thing with pcopy in, pcopy out, or pcreate. Device pointer does exactly what you would think. It returns a pointer to a variable on the device. This is just what I said, perhaps spelled out. Present or copy or pcopy, allocate and copy if needed, and copy back on host on exit. So again, pcopy is just like copy. It's overloaded. It means allocate, move over, operate on, move back, deallocate. Copy in means allocate and copy if needed. And again, there's no copy back, and there's no copy in when you use copy out. There's a lot of words in each one of those, but the concepts are fairly simple to grasp, I think. You are always talking about taking data from the host to the device and taking it back. Sometimes you only need to do part of that operation. And I think there's some slides later on taking advantage of the data that is already on the device that you can use for calculation after calculation without ever having to move it back to the host. The more you can do that, the better off you are from a performance standpoint. Okay, so maybe akin to that are a handful of hints for how to use these particular data clauses. So present is for variables that have been copied in, copied, or created up the call chain. So if you know up the call chain that you have some variable set not on the device, use the present clause, okay? If you don't do that, the compiler will copy the host version in when you're expecting the device version. So this is exactly, I think, the cantrip that you were just referring to. If I don't use present and yet I know the variables out there and I want to use the device copy, if I don't use present and there's a host copy that's dirty, it'll ship it out there and I'll get an incorrect result. So I think that's actually very germane to your question. Present or create, that's for variables that are only going to be used on the device. So startup information, constants that maybe are going to be used in future, I don't know, some constant tensor or some constant vector that are going to be used in subsequent calculations. You want to use present or create. And present or copy in, that's variables that must be copied in from the host. However, they do not change after the first copy in. So an intermediate result. So that's maybe the other side of it. Some intermediate result that changes at a different cadence. Present or copy in is going to help you get it out, but you're going to be responsible for managing the data and the coherence of the data yourself between the host and the device. You can, however, have data regions that actually span procedures. So you see first the subroutine up here called sub has two arguments A and B. We're going to present copy in B on the device and then actually ask the compiler to generate GPU code for this simple loop. Make sense to everybody? Then when I call subroutine bus, if I call sub from bus, okay, then I have a data copy of X, right? Because subroutine sum is expecting both of the variables to be living on the device. So I have to do a copy in inside bus, and I use the Y that's already on the device in subroutine sub. So it's a very complicated interleaving of the two data fields. But if you have a class of subroutines, that are only going to operate on device data, this is actually a fairly efficient way to do it. It means you don't have to do explicit copies every time. Okay, so more information about coherence between host and device. You can actually use update directives. You can update host data, and you give it a list of variables that you want to update on the host using device data. Or you can update the device with new host data going the other way. You have to be in a data allocate clause for an enclosing data region. This is an interesting, they can both be on a single line. You can say update host with a list of variables and update device with a list of variables. I wonder what would happen, and I'll leave it to you guys as an exercise, and I would love to hear what happens. If I give the same list for host and device, what happens to the data? Which one is the fiducial copy if I do that? It is undefined behavior, and I'm sure it's implementation specific, right? But I would love to see what the answer is, at least for PGI. I don't know. I've never tried that. And when I saw this bullet, I was immediately tempted to go try it, but then I was like, no, I'll spiral down the rat hole and I'll never figure it out, and I won't be able to give you a definitive answer. So please, if you get a chance, try it at the hands-on tonight. Try to do update host and device with the same list of variables. Okay? To me, just in general, this seems to be a very dangerous programming practice, right? To update host and device data on a single line. I think that's an easy way for human error to creep in. I would advise against it. Just because you can do something doesn't mean you should do something. And I think that's definitely in this category. And you can string together concepts. You might have noticed this already with OpenACC, right? There are a handful of concepts. There's device data, host data, kernels, loop scheduling, and then temporal things that have to do with that. Copy in and copy out, when device data is resident, when host data is resident. You can sort of almost string those things together. And you could almost guess what the directive is going to be if there's some job you want to do. And for example, you can update just when you copy in something, or update just when you copy out, for example. So this is an example of porting a sort of a large-ish program from PGI. You can go get it on the web. If you go to this PGI page, there's a link to this open source seismology program. You're solving the 2D or 3D isotropic elastic, viscoelastic, or poroelastic wave equation. Just a finite difference method, so it has a very simple stencil, finite difference stencil. You see the author's name. The accelerated source is taken from this one specific elastic finite difference code that's in the suite. And again, you can find the details at that link at the bottom, which is, I think, on the website for the school. So I took the slides from PGI on sort of how to do OpenACC programming using this example, and I've made one immediate edit, right? Their first question is my algorithm right for a GPU? Well, most of us do not have that luxury. In many cases, we have an algorithm that we know basically is going to be the only one that works, and we're going to have to make our implementation fit rather than making our algorithm fit the particular implementation that we're forced into. So I've restated this to what parts of my code are most amenable to computation on the GPU, because sometimes that's the best you can do. Well, this particular code has a big outer time step loop for finite difference time evolution, and 9 inner parallel loops. And it's already got some OpenMP threaded parallelism stuck in it. Their comment is this is a good candidate for the GPU, but not ideal. And the reason it's not ideal is because that the number of flops in each one of those individual parallel loop bodies is not that big, right? It's rather modest, especially compared to what you might want to do if you just wanted to write the fastest possible GPU code. So the first thing you can do is you can add compute regions. Well, the first thing to do is to simply do that around one of these triply nested loops using the kernels directive. And then with PGI anyway, and there's comparable flags for Cray and for HMPP, you can get a listing file. You know, what exactly did the compiler do? What CUDA kernels did it generate? Where did it think that it could do parallelization, and where did it give up and say it can't? And so that's the output from one of those. You can see that we've tripped minus ACC to trip that part of the compiler framework so that it actually looks for the ACC sentinels. And then minfo equals acceleration. Give me the info, give me the listing file with the accelerator information. And you can see, I'll go back up to the code for just a second. Well, it's not actually there. There's a bunch of variable declarations and a bunch of copy ins. So we're initializing data on the host and then copying it to the device. And all the compiler's telling us is it's doing that. Then it's looking at those triply nested loops. It got them all. It generated a single accelerator kernel over all of them. And it actually gives you what it guessed was the best default scheduling for those 3 loops. And then finally, you have to do a reduction for the total kinetic energy and the total potential energy over the whole grid. I'm sure it's just a check of total energy conservation for the entire code. And it generated reductions code for that. That's actually very valuable. To do that by hand with CUDA is not so trivial and get good performance. And in general, the OpenACC compilers I've seen do a good job of the reduction, which can be used in a variety of ways. So if you look at the initial timings, so just take the original code, run 2 MPI processes with 4 OMP threads. It takes this long. If instead I just run single-threaded but 2 MPI processes, same problem, it's 3 times slower. Awesome. So it's obvious that we want to be able to use GPUs. Now, people who have done GPU programming, if you've done GPU programming, I bet you've seen talks like this before. So everybody knows what the answer is. Why is it slower? The data. Moving the dang data over that little bitty straw of a PCI Express bus, right? That's the big problem. So again, all we did was put a big accelerator region around those triply nested loops. So everything is copied. All right? So every time we do an iteration of any of those loops, host data is taken, moved to the device, moved back after the iterate of the loop, saved, and then done again every time we trip the loop. Ridiculous amount of data moving back and forth. So we have to optimize the data movement in the language of this presentation. We do that by laying out an accelerated data region before we do the kernels. Okay? This is all new typing, it should be noted, right? Even though it's white, you see the sentinel at the front, the bang, $ACC. This is all new stuff, even for that little piece of code that was shown before. I have to list individually all the variables, basically, and give which one is the fiducial copy, either the device or the host, all right? If, for example, you do this in a Fortran code that uses modules to keep track of global data, this exercise for a large code can become very, very tedious very, very quickly, right? There are a handful of tools that are becoming available to help with that. I would say this is the hardest thing to do if you want to transition an extant dusty deck, let's call it, code to a GPU if it's of any size at all, and especially if it uses modules to store globals in Fortran. Okay, is scoping these variables from host to device in the way that you have to do it. If you've done this to a large MPI only code, and you've done this with OpenMP, you've probably encountered the same sort of problem, right? Scoping individual variables for OpenMP loops that are either going to be shared, thread private, or fully private is also the same kind of thing. So we make a nice list of what the accelerator data needs to be, put that in, and lo and behold, we've cut the time by almost a factor of 25 from the original GPU number. And now we're several times faster than the original MPI and OpenMP version as well. Just with that. Just leave the data where it needs to be. Don't copy it every time I go through the loop, right? That's all that that accelerator data part did. So for this nice triply nested loop with a large loop body, we've got a significant speed up. Now cast your mind back to this info slide where the compiler told us what it thought the best loop scheduling was. We can do another optimization. If we look at the scheduling it used, we can see that it didn't quite do the simplest thing. The K loop has the smallest loop bounds, right? The one you didn't know that looking at it, but I do, and certainly the compiler didn't know it, right? So it's much better to use vector scheduling for that loop and put the inner loop on gang. Okay, just change the scheduling because you got the lowest loop count on the outermost loop in this case. That's the thing that ought to be vectorized across rather than the inner loop nest. You get a modest improvement. And when I say modest, I mean very modest, 3%, right, by changing that scheduling, right? And most of that's because the body of that loop is pretty fat. There's enough flops there to hide almost any differences in scheduling that you might encounter. Now you have a code that runs 7 times faster than it used to. The claim was it took the guy who sat down and did this only 5 hours to do it. So my guess is that's probably true. But how do you translate that to yourself? He got to pick what code he wanted to work on. So he picked one that has nice triply nested loops, and that's almost all the flops. That's on the pro side. On the con side, it's code that he wasn't familiar with, so he had to pick it up cold, okay? So that's not so easy, so he probably had to invest some of that 7 hours into understanding what the heck is the code doing. But he also probably knew a lot about OpenACC and exactly the kind of pitfalls that can be reached. So I suspect that for this kind of code, where it's dominated by a very straightforward triply nested loop with a lot of stuff in the loop body, something of order 5 hours, 10 hours, something of order tens of hours is probably ample to be able to get good performance. But your mileage will definitely vary based on how many flops you actually have in that loop nest and how much of a contribution to the total cost of the computation in the code is actually embodied in what you can move out to the accelerator. One thing I haven't showed you yet is, and I encourage everybody to go do this, is to go online to openacc.org and download this quick reference guide, which you just print out. It's a PDF. You fold it up, and it basically has the entire 1.0 spec on a single double-sided card. And it's the whole spec. I mean, that's all there is. Now, it's terse, right, to make it fit on one 8.5 by 11 piece of paper front and back. But it's amazing to me how much information is actually on here and can easily at least lead you to ask the right question, if not give you the answer every time. You've heard about CUDA. You've heard about OpenCL. We've talked a little bit about OpenACC. You've also added to this toolkit that you've assembled over the past week. You've talked about MPI. You talked about OpenMP. Have we talked about PGAS languages at all? Yeah. Or at least obliquely, right? So there are all these different ways that we can attack an individual problem that has some sort of inherent parallelism, right? Don't get into the trap of thinking you're only going to use one. And I think that was part of the theme of Bill's talk today. Don't get into this trap that you're only going to have to use one. And in fact, you're going to have to use more than one. But what that presupposes is that each of the individual programming models that you do make use of can easily interoperate with others, okay? Now, because OpenACC is an emerging standard, right, lots of things don't work quite right? I think that's less true than it was even 6 months ago. I think it's sort of hard to find a compiler bug in an OpenACC compiler. It's probably just as hard as it is to find a compiler bug in a compiler nowadays. Okay, both PGI, Cray, and HMPP have done a really good job in smashing a lot of those bugs. But you still may have to use other programming models to get the job done. So for example, if you work on a code where somebody's taken a particular kernel, rewritten it completely in CUDA, because that's what they could do 2 years ago, and you'd like to make use of that kernel in a code that you're writing that's primarily OpenACC, wouldn't it be cool if you can do that? Well, the good news is you can. And part of the reason is CUDA, OpenCL, OpenACC, they all have to adhere. They're mostly built around this notion of having a CPU, a host, and a device. And the device has some memory attached to it that's fast, and you have to manually manage the memory between the device and the host. Okay? Because that notion is universal across all those programming models, they in fact do interoperate pretty well together. So you saw earlier simple CUDA-C code. This is a really simple CUDA-C code, right? So you take standard C over there on the left for just a SAXPY, okay? So just take a vector and multiply it by a scalar everywhere, okay? And then if I do it in parallel CUDA-C over here on the right, then all I've done is pre-calculated my indices that are needed, do the CUDA min copy for X and Y, perform the multiplication on the device with the right numbers of blocks and threads, and then return it back to the host. But what if I wanted to write an OpenACC main and then use that same C kernel for the SAXPY? So I've already written a kernel in this previous one. You don't see it here, but I'm assuming that I have a SAXPY device kernel already written in CUDA. I don't want to have to reinvent that wheel, right? Here it is, as a matter of fact, written in CUDA, all right? Instead of doing CUDA memcopy and CUDA memcopy back in the main, I can sort of keep it portable by using OpenACC directives like accelerated data, where I initialize X and Y, use the device data when I get over there, and then close the data regions and therefore make the copy back, right? So now this driver is completely portable. If I call SAXPY and I have two implementations of it, one written in CUDA, another written in OpenMP, another written in whatever, Chapel, it could be even, then I don't have to change any of the driver source code. All I have to do is change the implementation under the covers, change a line in the make file likely, to go from one platform or one programming model to the other. That works. I don't know why you would want to, but you can do the reverse, okay? You can start with a CUDA-C main and write the SAXPY in OpenACC and call it from the CUDA-C driver. I suppose there's a corner case where you would want to do this. I don't know what it is. You can do the same thing with what's called CUDA Fortran. CUDA Fortran is a implementation that's only available via PGI. It's basically just a direct mapping of the CUDA extensions to C to Fortran. A lot of CUDA Fortran code has been produced over the past couple of years because CUDA Fortran was available long before OpenACC and before most of the directives-based approaches that were hatched before and during the birth of OpenACC, like the PGI accelerator directives and the HMPP directives. So CUDA Fortran has been around for a while, and there's lots of CUDA Fortran scientific computing code, so people jumped right in. For example, does anybody do climate here? Climate guys, for the most part, write in Fortran. They've got a lot of CUDA Fortran code already written. So it would be nice to be able to leverage all that. Well, you can in fact do that. There's the standard Fortran driver. To do parallel Fortran, you just have to do some declarations like you do with CUDA-C. You give the device variables a new attribute when you declare them as real, and then actually launch a CUDA kernel exactly like you do in C. You can replace that CUDA Fortran kernel. Well, here's the CUDA Fortran kernel that you actually called, but you can call it from an OpenACC driver the same way as you did with CUDA-C. Though I don't know why you'd want to, you can do the reverse. You can call individual OpenACC from a CUDA Fortran driver. I would suggest go ahead and investing a little bit of time to change the driver over to OpenACC, because CUDA Fortran is certainly not portable. So there's a note here that says, in theory, it should be possible to do the same with C and C++, including thrust, but in practice, compiler incompatibilities make this very difficult. I think that's an understatement. You can get interoperability with thrust, but it's not without significant effort and perhaps is not worth the trouble that it takes. You can call libraries that expect device data or host data. The one thing with a lot of libraries, especially linear algebra libraries, is they expect the data to be on the host and they will do the copy for you. Furthermore, they will only do the copy if, after analyzing the trip counts that they're going to have to do, for example, the matrix vector multiplies, that you're going to gain by shipping the data out to the GPU and then shipping it back, right? If you're going to get enough of a speed up out on the GPU to amortize that cost, then they'll do it that way. Otherwise, they're going to keep it on the CPU. So if you just use the regular old interfaces to a lot of linear algebra packages that are seemingly accelerated, that's the kind of thing that you'll end up with. Same thing. There's lots of accelerated libraries that you can use. Almost all of them work when you stick them into OpenACC code. Cray's libsi is another example of that. How to play well with others. My advice is the following. Start with OpenACC, expose the high-level parallelism, ensure the correctness of the code that you're writing without having to change any of the leaves, if you will, any of the subroutines underneath, and optimize away the data movement last. So go through the steps that were in that one example. Put the compute constructs in first, see what obviously slows you down, and then go back and put in the data constructs. And leverage other work that's available. You want to use libraries if they're available, which may mean placing data out on the device so that the libraries can make use of the data straightforwardly. And lots of CUDA already exists. You should have lots of CUDA kernels probably to choose from for a variety of tasks, and it'd be nice to be able to reuse those. And you can with OpenACC. Then there's a piece of advertising there to ask you to share with others. You can also interweave OpenMP and OpenACC. It's far from impossible. Let's say I have a piece of parallelized code via OpenMP that looks like this, where I call a subroutine in parallel that contains OpenMP, and I call a couple of serial subroutines, but I put them inside an OMP do loop, call a communication via MPI, for example, and do yet a third OpenMP routine. I can go into that same code and stick in some ACC Sentinels as well. For example, I can copy in to the device the OpenMP shared data, then present or create the OpenMP private data. Now this kernel is assumed to contain both OpenMP code and OpenACC code, and I've handled the data for that part of it with these two Sentinels. And I have an ACC parallel loop around these calls, which didn't contain any OpenMP. Now I'm going to put them out on the accelerator. Maybe I can even do it asynchronously, and then do the second part of the OpenMP that doesn't touch any of the accelerator data. And there's a couple of ways to do this. Again, you can do it asynchronously by adding this async clause, but that's a little bit trickier and something that we don't have time to go into today. All right, so I wanted to end with sort of pointing everybody towards OpenACC 2.0, which should have compliant compilers available within the next month or two. If you have access to a Cray, it should be in the Cray compiler next month, and if it's a PGI compiler that you have access to, then it'll be probably a couple of months, but no longer than that. The big highlights in my mind are now procedure calls can be done, and you can do it in separate compilation units. You used to have to inline subroutine calls, for example, if you wanted them to span be inside a compute construct. Now you don't have to do that. You can do nested parallelism, and I'll show you an example of that. There's this loop tile clause. So the one thing you might have noticed is I can schedule gang, worker, vector, but they're 1D entities, right? I don't have the power to go to multiple dimensions like I do if I do a kernel launch in CUDA. I'm going to mimic that with this loop tile clause in OpenACC 2.0. Data management features and global data, a bunch of other good stuff. So first, procedure calls. So now, if I call foo inside a loop, what I need to do, I would have to inline foo to be able to let it span inside that parallel region. Now I can have it in a separate compilation unit where I tell the compiler what the parallelism of foo is. So I set this pragma ACC routine worker where each iteration of the call to foo is going to be ascribed to a OpenACC worker. And then that loop can actually be made parallel with a gang over that parallel loop on the left, and each one of the calls to foo being assigned to a worker inside that gang using the code on the right. Further, I can do something else. I can make the stuff, instead of just using routine worker over here on the right, I can explicitly break up the loop that appears in foo and launch a kernel from a kernel, effectively, every time I call foo. I don't know this for a fact, but I suspect this requires a higher CUDA compute capability than is present on Keeneland. You probably have to have at least CUDA 5 capability to be able to do this sort of nested parallelism. You certainly have to have that to do it in CUDA. So this example, even if you had a 2.0 compiler, probably wouldn't work on Keeneland because of the age of the GPUs that are in it. You'd probably need something newer with like a Kepler. The loop tile clause looks exactly like you might expect. If you can recall from, what was it, 4 days ago when Jeff started this talk, where he told you how to do CUDA launches, it's exactly like you would expect. You know, block the loop into 8x8 tiles, exactly like a CUDA kernel launch. There's also support for putting in device-specific tuning, where you can say if the device type is in some sort of NVIDIA, make the number of workers 256, but if it's a Radeon with slightly lower powered and lower capability GPU cores, you want to go up to 512. That way you can make one sort of cradle file for all the platforms you'd possibly want to run on and have platform-specific optimizations without having to do it by hand. The point is, and we didn't talk about async at all because we didn't have time, but you can launch kernels from OpenACC asynchronously. You launch the kernel, the host code keeps going, okay? You can do even more crazy things, right? You can launch a kernel asynchronously, do some computing on the host, launch another kernel asynchronously, give it a different handle, so now there's 2 kernels running, perhaps, at the same time. Launch another kernel. If you use the same handle, this one has to complete before this one completes. That's sort of easy to see, but what if I add this line, where I wait for the first asynchronous kernel to finish? Well, that's going to block all of the host code, because the host is going to sit there and wait for data to be returned from handle 1, okay? And it won't launch the next parallel sync with handle 2 until it gets ready. So perhaps this hasn't finished, but both these have. Maybe I put a lot of work in handle number 1, but these guys haven't finished at all. What would be nice is if I can block on waiting for 1 for the host code, but go ahead and let the next guy in line execute on the device, right? There's no way to do that in 1.0, but in 2.0, you can add an async handle to the wait and tell the compiler which one of the asynchronously launched kernels you're actually waiting on, and therefore it won't block on everything. There's a bunch of new API routines and expanded interoperability, including with the Xeon Phi. So all of these new 2.0 compliant compilers should be able to target Xeon Phi processors. HMPP already does. Finally, the hands-on examples. If you go to this GitHub address, there's a bunch that we used at an Oak Ridge Leadership Computing Facility OpenACC workshop last week, 2 weeks ago. And the 2 examples that are especially good are this VH1 example, which is an astrophysical hydrocode that's pretty simple, and this Hymeno example. And if you Google Hymeno and OpenACC, you'll find a ton of work on that particular code under OpenACC. And that's all I've got. Does anybody have any last questions?